Now, as I increase the energy further, I'd like you to notice what's happening. As I continue increasing the energy, I get more and more of this downward curvature, and that tends to move or pull this node inward. Two things actually help contribute to that. The first is that I've got less and less actually curvature in this forbidden region, so I come in here with a little bit less slope. That helps me curve around more as I make my curve. And secondly, I just overall have more curvature, so all of those factors combined tend to move this node here inwards. And I can continue in that continuous way, increasing the energy. That node keeps sliding inwards, and I still have this very bad exponential divergence that I don't like. But as I continue along, what you will notice is that eventually I pull the node now into the classically allowed region over here. And as a consequence, I then can, once I cross the axis, I can start to curve back toward it. And as I continue doing that with more and more curvature, I start to get to a point where now I'm beginning to inject into the forbidden region toward the axis. And that allows me then to mitigate that exponential growth. And I'm about to, somewhere around here, find a perfect balance point where I have an energy just before I cross the axis. Right? This one isn't perfect. You'll notice I actually did happen to pick an energy with a node, but this is pretty close to that perfect balance. And somewhere in here between this frame and this frame, if I go backwards, somewhere in there between those two, I've got that perfect energy. That then will take me to my second state, or what is typically called the first excited state. And this first excited state, I'd like you to notice, it occurs once again just before I've introduced now a second node. And the state itself, because it's the last state that has just one node, actually has one valid node. Now, if I continue increasing the energy, what you will see is once again, I'm now pulling both of these nodes inward, right? They continually, right? And then eventually I pull the node here again into the classically allowed region. And as I do that, right, I then can cross the axis and curve back down toward the axis, and eventually I can inject something with just the right amount of energy. Boom, up, went a little too far. I will get then another excited state, and this new excited state now, of course, has two nodes, right? It has this node that's been pulling in from the first excited state, and it has, I'm sorry, I know this is getting a little messy, it has this second node here, right, which had originally been the node that represented that nasty crossing. Here, I'll go back. That nasty crossing of the axis right around, whoop, went too far. Right here, I almost a solution, then I have that nasty crossing right here, and that nasty crossing keeps pulling inward, and eventually, if you're watching where it is going to become perfectly just my favorite. There, just past it, right there, it becomes a new node in my next state. So now I think we can draw our final conclusions. Just before we do that, it's always fun, I think, just to play the movie for you here so you can kind of see the overall behavior that we've been discussing. If I play this here as a video, you'll notice basically this thing wags around like a tail, and it's really the wagging of this tail back and forth, and every time that tail goes perfectly horizontal, that's when I have a solution. So, our next set of conclusions go as follows. Each new state, but I'm going to again borrow terminology from waves. These states and waves are usually called modes. Each new mode, and I like to do it this way to make a poem so we can remember it, but each new mode has one more node. Now, if you want to be more mathematical about it instead of a poem, what we're saying is that if we do E sub n, where n starts its value at 0, like any good C++ or programmer would use, right? Then E sub n, it has exactly n nodes. So E0 has no nodes, and then each subsequent state has one more node. The other last comment I would like to make is that En, right, is in fact the last solution with n nodes, right? Because as soon as we go put the energy just a little bit higher and generate that n plus 1th node, we will be diverging away in the forbidden region, and we have to wait to curve things back around to get to then the next node up from there. So En is the last solution with n nodes. And finally, there are no solutions close to En, right? If I increase it just slightly, I get that extra node, and that blows up to infinity. If I decrease it, I'm not. End up diverging away from the axis. So there are no solutions close to En, and this ultimately is the origin of the discreteness of the solutions. Now, many of you, I'm sure, are familiar with these type of mathematical boundary value problems where we have boundary conditions on two sides, and it's very common to find these types of eigen functions and discrete eigen spectra coming out. So it's really the story that you may have seen in some of your math courses about what happens when we apply boundary conditions to eigenvalue equations. But I'd like to go through this discussion so we can really see why that arises and how it does, because it has taught us, in fact, a number of general lessons. Very good. So for now, this is the end of general lessons. There will be more that we can draw out of the the finite square well solution. But now I'd like to turn back to the specifics of our square well and begin to learn then how do we actually solve to find the precise values of the energy, getting away from this qualitative picture and becoming then more quantitative.